Hello, my name is Mikolaj Wozniak. I'm a third year computer science and mathematics student at the University of Warsaw. My project is about dynamic sample weighting for time series foundation models pre-training. My mentors are Mikolaj Wozniak and Artur Dubravsky from Autonab. Motivation. During training, every series are treated equally. But some are irreducible noise, some are already fit, and some are still improving. So we want to leverage those differences and train on the samples that can give the model the best training accuracy and score. It was well studied for large language models pre-training, but largely unexplored for time series foundation models. So our goal is to create a difficulty metric measured throughout training for data balancing to improve sample efficiency and locating capability gaps where synthetic augmentation helps post-training. Our setup is M competition monthly subset, which is a popular competition for time series forecasting. We will take subsets of each of those competitions, around 400 or 500, to make them equally sampled, and we will take horizon 6 and context 12. We will do it on 3 seats. Our model is patch TST with hidden layer size 256, 4 layers and 4 heads. We use patch 8 and review normalization. We use Adam W and quantile loss over 9 quantiles. Our pipeline looks like this. First, the model produces signal, which is loss, gradient, or at the beginning of a training, we can produce some static one. Then we calculate a metric, which is mapped to a distribution by a policy. Then we upweight samples, and they are sampled with probability proportional to weight. Training continues. Such refreshes are happening every case steps. Now we can move to our weighting policies. The first one is softmax. We also do standardized softmax to make sure that no samples will be starved, because some signals are very strong. For example, gradient can explode, or we also do proportional one. First batch of metrics are static loss based. We use variation of a series, so how it changes. It is a static one. We also use loss with both proportional and softmax after, and we use moving average of loss improvement. So we calculate how the loss changes, and the samples that changes a lot in the good direction are upweighted. We then compute moving average of this score with some parameter b. We also have gradient metrics. The first one is gradient magnitude, which measures how strong is the signal, how strong is the gradient move, and the second one is just a gradient variance, measuring how gradient does differ during training. Our hyperparameters are temperature 1 and the beta is 0.8. We refresh around every 500 epochs. We use MAE, but scaled by standard deviation of the series, and CRPS, also scaled by standard deviation of the series. We use 9 quintiles. So the only strategy that was able to improve was loss improvement moving average with softmax applied after. All the other ones were performing worse, where gradient variance and gradient methods were much worse. Now let's look at the pair domain improvement. We can see that the improvement or decrease was quite similar across domains. We can see that tourism was the hardest ones, and it made softmax loss and proportional loss and softmax loss achieved a very bad result there. And we can see that the gradient variance was bad across all the domains. We can also not see, but it was conducted in a training, that the variance of acids was quite big, so there was a big noise generated. So the experiments varied a lot in the score. So some results and the preliminary results that we have right now is that weighting mostly doesn't help, or dynamic weighting isn't really helping much because it will produce much noise, and 6 out of 7 strategies didn't work. Usually learning progress wins, so we have so measuring how is the loss changing is the best strategy right now, and seeds are noisy, so the variance between the experiments are big. I would like to thank Mikolaj Wozniak and Professor Artur Dubravsky for mentorship throughout this work, the members of the Autumn Lab for insightful discussion and continuous support, and to Rachel Burci and John Nolan for organizing the RIS program and creating this opportunity. Thank you very much.